A ship's propeller can spin in salt water for 25 years, 24 hours a day, and come out of dry dock without a single trace of rust. Across the global merchant fleet, over 50,000 of these propellers are submerged in seawater right now, one of the most corrosive environments on the planet. But naval engineers aren't relying on luck. So what is actually keeping these propellers from dissolving away? The answer involves an alloy that cannot rust by definition, a hidden electrical battery that forms inside every steel-hulled ship, a sacrificial piece of metal whose entire job is to die first, and an industry that spent a century turning basic chemistry into a defense system. To understand why a propeller survives, we must first define what actually happens when metal decays. In casual conversation, rust is a generic term for any corroded metal. But in chemistry, rust has a strict and exclusive definition. It is hydrated iron 3 oxide. This specific compound only forms when elemental iron is exposed to oxygen and water. The chemical pathway requires free, unalloyed iron at the very surface of the material to initiate. Without metallic iron, classic red rust cannot form. It is chemically impossible. This is why a steel hull degrades while the propeller remains clean. Standard ship hulls are fabricated from carbon steel, which is packed with free iron, making it highly vulnerable to the sea. A propeller made of steel would invite rapid, catastrophic failure under these conditions. To prevent this, marine engineers bypass the iron oxide pathway entirely by selecting non-ferrous alloys for the propeller casting. It is the chemical equivalent of trying to start a fire without any wood. Other elements like copper, nickel, or aluminum still react with seawater, but they do not produce the flaky, porous red crust that degrades steel. Instead, they play by entirely different chemical rules. But if these non-ferrous metals still react with seawater, how do they protect themselves from dissolving? The modern answer to this challenge is cast nickel aluminum bronze, a specialized copper-based alloy engineered specifically for high-stress marine environments. In maritime manufacturing, this material is governed by strict specifications: ASTM B148 for sandcast components, and ASTM B369 for centrifugal castings, typically designated under the Unified Numbering System as C95800 or C63000. Within these standard grades, the chemical composition is tightly controlled. The alloy contains roughly 9 to 11% aluminum and 3.5 to 6% nickel, built upon a base of copper and small additions of iron and manganese. It is this precise chemical blend that dictates how the propeller surface interacts with the surrounding ocean. Instead of decaying, when exposed to salt water, the aluminum within the bronze reacts instantly with dissolved oxygen. This rapid reaction creates a dense, non-porous, passive oxide film, primarily composed of aluminum oxide, measuring just 50 to 200 nanometers thick. To put that in perspective, this molecular protective barrier is roughly the thickness of a single sheet of household plastic wrap. If sand, debris, or cavitation bubbles physically scrape this film away, the exposed aluminum instantly reoxidizes. It is a completely self-healing system that continuously seals the metal against further dissolution. This microscopic layer allows a multi-ton nickel-aluminum-bronze propeller to operate for decades without ever suffering the red structural decay that plagues carbon steel. Yet, selecting the ideal metallurgy is only the first step in protecting the ship's stern. While this bronze alloy resists general corrosion, its very presence next to a steel hull creates a new set of electrochemical challenges beneath the waterline. Submerging a multi-ton bronze propeller on a steel ship reveals a hidden electrical mechanism that surprises almost everyone. The propeller does not exist in chemical isolation. Instead, the moment it is bolted to the steel shaft and submerged, it becomes part of an active electrical circuit. Seawater, rich in dissolved salts, acts as a highly conductive electrolyte. In the marine galvanic series, metals are ranked by their electrical potential. Clean carbon steel registers a potential of -0.60 to -0.71 volts, while nickel aluminum bronze sits in a far more noble position, between -0.31 and -0.42 volts. This voltage gap of roughly 300 millivolts turns the entire stern into an unintentional galvanic battery. In plain terms, the ship's steel hull acts as the negative terminal, or anode, while the bronze propeller becomes the positive terminal, or cathode. As electrical current flows through the seawater, the active steel hull corrodes, sacrificing its own metal to protect the noble bronze. The propeller does not rust because the massive steel ship is constantly donating electrons to keep the bronze intact. But while this accidental battery spares the propeller, it introduces a severe threat to the surrounding hull plates, which now face rapid localized destruction. In the late 19th century, as shipbuilders transitioned to steel hulls while retaining copper alloy propellers, they quickly observed a localized pattern of destruction. Royal Navy technical notes and Lloyd's Register circulars from the 1890s documented severe, intense pitting concentrated almost entirely around the stern. Steel hull plates, rudder fittings, and structural rivets adjacent to the bronze propellers were degrading at rates that defied standard wear models. The electrochemistry of the marine galvanic series explained the mystery. By coupling the noble bronze propeller directly to the steel hull through the propulsion shaft, engineers had completed a massive electrical circuit. In this wet environment, the steel hull acts as the anode, sacrificing its own metal to keep the cathodic bronze propeller pristine. Modern TOEFL-type electrochemical studies confirm that even modest steel-to-bronze surface area ratios can accelerate the local corrosion rate of adjacent steel several-fold. The propeller survives because the surrounding ship is literally dissolving to save it. It is the engineering equivalent of keeping a lock pristine by letting the vault door rust away. Protecting the drive gear comes at the direct expense of the hull. How did marine engineers stop this self-inflicted destruction without abandoning high-performance bronze? Here's the part that catches people off guard. The most critical defense against stern corrosion has nothing to do with the propeller alloy itself. Instead, marine engineers completely rewrite the electrical circuit of the stern using dedicated cathodic protection. To protect the steel hull from the noble nickel aluminum bronze, shipbuilders bolt blocks of highly active metals like zinc or aluminum directly to the stern frame and rudder post. These sacrificial anodes are roughly the size of a car battery. Because zinc and aluminum sit far lower on the galvanic series than steel and bronze, they become the active anode in the system. In plain terms, these parts are chemically engineered to die first, dissolving into the sea to keep both the hull and propeller intact. For larger vessels, engineers employ impressed current cathodic protection, ICCP. Instead of relying on passive metal decay, ICCP systems use a dedicated power source to drive a low-level DC voltage, typically between 2 and 5 volts, through inert titanium anodes mounted on the hull. This tiny electrical current effectively reverses the natural corrosion pathway, neutralizing the galvanic currents before they can strip metal away. But how do operators ensure these sacrificial blocks and electrical currents actually survive the brutal reality of years at sea? The integrity of this underwater defense does not rely on goodwill. It is enforced by international maritime authorities. Classification societies like Lloyd's Register, DNV, ABS, and Bureau Veritas establish the rules that keep these hardware systems operating. Under these regulations, sacrificial anodes must undergo formal inspections on a strict cadence, typically synchronized with the dry docking cycle every 2.5 to 5 years. Once an anode loses half its original mass, its ability to supply a protective electrical current drops significantly, requiring immediate replacement. The rules leave no room for compromise. But commercial demands can tempt operators to delay these scheduled shipyard visits, and breaking this service rhythm triggers immediate consequences. Without active anodes, the galvanic current begins stripping metal from the next easiest target. Pitting spreads rapidly across the propeller shaft and the surrounding steel hull. This localized decay soon threatens the shaft seal assembly, which keeps seawater out of the ship's internal machinery. If seawater breaches these seals, it corrupts the lubrication system, risking immediate propulsion failure. Neglected maintenance invites mechanical failure. A compromised shaft seal or severe hull erosion leaves operators with no choice but to order an unscheduled dry docking. While a standard set of replacement zinc anodes costs around $30,000, emergency dry docking fees, replacement parts, and lost operational time can easily cost an operator over $2 million. This stark economic reality transforms basic maintenance from a simple chore into a vital financial shield. This financial math dictates every major decision in commercial shipbuilding. When a new vessel is designed, naval architects and operators look past the immediate price tag of the raw materials. Casting a premium nickel-aluminum bronze propeller and installing its associated cathodic protection hardware requires a significant capital investment. For a large merchant vessel, this specialized copper alloy casting represents a steep upfront cost. But when classification bodies and fleet managers calculate the total cost of ownership over a 20-year operational life, that initial expense is minor compared to the alternative. A single incident of unscheduled dry docking to repair a corroded shaft seal or patch galvanic damage on the hull plates can halt operations entirely. The resulting operational interruption wipes out profit margins through charter losses, emergency shipyard fees, and extensive hull-side steel replacement. By comparing these long-term risks against the cost of premium metallurgy and regular anode maintenance, the industry arrived at a clear verdict. The math was settled decades ago, and it was not close. Spending more during the construction phase to secure a corrosion-resistant stern assembly prevents even the smallest risk of catastrophic failure down the road. It is a highly calculated long-term compromise where steep upfront hardware and material costs purchase decades of predictable, completely uninterrupted service. So what changed? During the mid-20th century, rising fuel prices and steel costs sharpened the economics of global shipping. At the same time, major classification societies like Lloyd's Register and various flag states tightened their survey regulations, raising the financial penalties for unexpected dry dockings. Before this shift, shipbuilders commonly relied on plain brass or manganese bronze propellers. In active service, these early alloys quickly revealed the limits of the older standards. Seawater systematically stripped the zinc from the brass matrix through desensification, leaving behind a structurally compromised, spongy copper framework that easily fractured under operational loads. These failures often occurred without warning, leaving vessels stranded. Meanwhile, intense cavitation at the blade tips physically tore away the metal, drastically shortening propeller life and reducing propulsion performance. As the post-war shipping boom demanded larger vessels, faster speeds, and longer transoceanic voyages, fleet operators could no longer accept these recurring mechanical failures. The industry required a durable, highly reliable standard capable of resisting both chemical degradation and intense physical erosion over years of continuous operation. This operational necessity forced shipyards to abandon zinc-rich alloys. By the mid-1960s, marine engineering shifted decisively, establishing nickel-aluminum bronze as the universal standard for merchant shipping. The older alloys had demonstrated their weakness in service, proving that cheaper upfront materials resulted in far higher long-term operational costs. Modern high-performance metallurgy became an absolute economic necessity. Deploying nickel aluminum bronze is only the first layer of defense. In practice, shipyards combine this metallurgy with three active protection methods. The simplest approach uses sacrificial zinc or aluminum anodes, bolted directly to the stern frame, which dissolve over a 2 to 5 year cycle to protect the steel. For larger vessels, operators install impressed current cathodic protection, or ICP. This system uses reference electrodes and titanium anodes to drive a controlled low-level direct current voltage through the wet hull, neutralizing galvanic currents. To support these electrochemical defenses, shipyards apply high-performance epoxy barrier coatings, like Jotun Penguard Express, to the hull plates immediately surrounding the stern frame. This localized shield blocks seawater contact and reduces the electrical demand on the anodes. Yet even this combined multi-layered defense has a hard physical limit. While anodes, electrical currents, and epoxy coatings successfully neutralize galvanic and uniform corrosion, they are completely powerless against the mechanical violence of cavitation erosion, tearing at the spinning blade tips. Maintaining this active chemical shield requires constant manual human intervention. For ship operators managing tight global logistics, taking a massive vessel out of service is a heavy commercial penalty. Delays cut straight into operating margins. Can you blame them? The day-to-day pressure to defer dry docking and keep cargo moving often clashes with the routine maintenance burden of inspecting and replacing depleted anodes. But ignoring these eroding blocks of metal creates a silent, unseen vulnerability. While postponing shipyard service might save immediate operating capital, a neglected anode quickly exposes the stern gear to galvanic current, quietly stripping away the structural integrity of the entire propulsion assembly. It is a constant tug-of-war between short-term commercial flow and long-term mechanical reliability. Engineering continues to evolve through quiet, incremental refinement. Shipbuilders now deploy super duplex stainless steels like UNS S32750 for specialized stern gear components, while real-time sensors monitor electrochemical potentials at sea. Even experimental carbon fiber composite propellers undergo trials to eliminate galvanic loops. Yet these alternatives carry steep manufacturing premiums. The steel hull paired with a nickel aluminum bronze propeller remains the dominant global standard, keeping cathodic protection essential. Back in dry dock, this pristine bronze represents a calculated system-wide compromise that keeps global trade moving. Subscribe for more engineering insights. Back in the quiet of the dry dock, that gleaming bronze propeller stands as a testament to calculated sacrifice. It survives not by resisting the ocean, but by orchestrating an electrochemical battle where zinc and steel decay so the blades can spin. In global commerce, perfection isn't the absence of wear, it is the mastery of it. Subscribe for more engineering insights.